Welcome to the Deep Dive, the show that takes complex technical blueprints, massive architectural decisions, and some pretty dense source material, and delivers the core actionable knowledge you need to master it.
Today, we're on a critical mission. We're defining the absolute foundational architecture for modern enterprise cloud infrastructure. We're going deep into the design principles for VMware Cloud Foundation 9.0, specifically how it integrates Kubernetes using vSphere with Tanzu.
And our sources for this, they're pulled from a pretty advanced architectural knowledge base. Think of the material built for something like the 3V0-24.25 certification. This is really about knowing the rules of the road.
Exactly. And it's not about just memorizing, say, 60 questions. It's about understanding the core logic behind the right answers. We're here to translate those high-stakes design choices into, real operational and architectural knowledge for you.
Okay, let's unpack this. We've organized this whole blueprint into four main themes. First, we'll establish the absolute necessity of foundation and high availability. Then we're going to map out networking and isolation for multi-tenancy.
That's a big one.
Third, we get into the application heartland, data, storage, and security governance. And finally, we'll look at scaling and operational observability.
Sounds good. Let's do it.
Let's start with resilience, the absolute bedrock. When you're deploying that Kubernetes control plane, what VCF calls the supervisor cluster high availability is, well, it's everything.
It is.
So if we're running this in a VCF 9.0 multi-zone setup, what is the hard, non-negotiable minimum number of vSphere zones you need?
The required minimum is 3 distinct vSphere zones. And that really is the first and most critical design decision. It's completely non-negotiable for a production-grade control plane.
Okay, but why 3? I think this is where people get tripped up. If a zone is an isolation boundary, why wouldn't 2 be enough, for redundancy?
Right, and that's the classic distributed systems question.
Yeah.
It's because the principle of quorum and consensus. The control plane uses systems like etc. to maintain its state, and it must be able to get a majority vote to operate.
A majority vote.
So with 2 zones.
With 2 zones, if you lose one, like a power outage, a network partition, whatever, you've lost 50% of your votes.
Yeah.
The remaining zone can't form a majority by itself.
So you get a split-brain scenario.
You get a split-brain scenario. It leads directly to a failure state. 2 zones, paradoxically, guarantees instability if one fails.
Ah, okay. So 3 is the magic number.
3 is the magic number. It lets the system tolerate the complete loss of one zone because the remaining 2 still constitute a majority. 2 out of 3, that's the design foundation that keeps everything running. It's just, the cost of entry for real HA.
That structural resilience makes perfect sense. So let's move to organizational resilience. Workload management. VCF is really strict about separating concerns.
Very strict.
If we want to host our production Tanzu Kubernetes grid clusters, where do we have to enable workload management?
It has to be enabled within a designated workload domain cluster. And this really gets to the core of VCF architecture, right? The whole management domain versus workload domain split. But I can hear someone with a smaller environment asking, why not just enable it in the management domain, save on hardware or licensing?
That's a great architectural question because it forces you to think about the operational risks. The management domain is, it's sacred ground.
Sacred ground, I like that.
It's strictly reserved for the core infrastructure services vCenter, NSX managers, the SDDC manager, and critically, the VCF lifecycle components.
So if you put workloads there, you're introducing chaos.
You're introducing application chaos, developers deploying apps that might hog resources or introduce weird dependencies or just need disruptive updates.
Right.
You risk resource contention, sure, but the bigger risk is you compromise the stability and the upgradability of your entire VCF foundation. The workload domain exists to absorb that churn. The separation isn't just tidy, it's mandatory for VCF to work properly.
Here's where it gets really interesting for me. We're moving from structural design to security and multi-tenancy.
In a big enterprise platform, you've got multiple teams, multiple tenants, all running on the same hardware. How does NSX provide that crucial network isolation between different vSphere namespaces? How do you make sure tenant A can't talk to tenant B?
It all comes down to microsegmentation. It's a cornerstone of zero trust. And the key mechanism is by creating unique network segments and distributed firewall rules for each namespace.
So we're talking about logical segmentation, not physical air gaps. It's all enforced in software at the kernel level.
Exactly. And the advantage is that granularity. NSX gives each namespace its own dedicated logical network, its own identity. But the magic, really, is in the distributed firewall, the DFW.
Because the rules are enforced right next to the workload.
Precisely. The DFW rules are pushed down directly to the ESXi host where the workload lives. So security policy is enforced right there, which means you can control traffic not just between namespaces, but even between pods in the same namespace. It's so much better than a traditional perimeter firewall for that east-west traffic. That is powerful. And that idea of isolation gets extended with the virtual private cloud model, the VPC, especially in VKS. What's the fundamental purpose of a VPC in this context?
A VPC is used to provide a self-contained, isolated network environment for a group of clusters.
I want to push on that a little. When I hear VPC, I think of the public cloud with totally isolated IP ranges and routing tables. Is VKS doing the same thing here, or is it more of a conceptual wrapper?
It's doing both. And that nuance is what matters for enterprise architecture.
Yeah.
It really does define an isolated networking boundary. Think of it like renting a secure mini office park inside the main data center.
Okay.
Inside that office park, the tenant has control over their own routing, their security groups, their IP space, but it's all completely segregated from the next tenant over. It's foundational for secure, scalable multi-tenancy inside VCF.
Let's focus now on the heart of it all, the applications. Data, storage, security. So, apps on Kubernetes need persistent storage. In a vSphere with Tanzu world, when a developer writes a YAML file asking for storage space, what does that persistent volume claim, that PVC, actually represent?
The PVC represents a declarative request for storage resources by a user or application.
A request. It's not the storage itself. It's the developer basically saying, hey, I need some space.
Exactly. And it's a critical abstraction layer. The developer just declares what they need: the size, the access mode, and most importantly, the storage class.
And the storage class is the bridge to the infrastructure.
It's the interface. When Kubernetes gets that PVC, it looks at the storage class, which might define performance tiers or deduplication, things like that, and it automatically provisions the right persistent volume on the vSphere side, mapping it to a VMDK. The developer never needs to know if it's on flash or spinning disk. They just know they got the gold tier they asked for.
So it's completely self-service. Okay, shifting to security. Let's start at the source. The container image. If you integrate a registry like Harbor with VKS, what's the primary advantage of its built-in vulnerability scanning?
The biggest, most immediate advantage is that it helps identify and block the deployment of insecure container images.
Huh?
It's an image governance checkpoint.
So you're stopping vulnerabilities before they even get into the cluster. How does that work? Does Harbor just flag it, or does it actually stop the deployment?
Oh, it actively prevents it. This is where policy enforcement is so critical. Harbor scans for known CVEs. So an organization can set a policy like no image with a critical CVE can be deployed.
And then the admission controller just rejects it.
The admission controller, informed by Harbor, intercepts the request and stops the pod from ever starting. It stops the security problem right at the gate.
That handles the image. But a clean image can still be deployed insecurely. Which brings us to pod security admission, or PSA. What's its fundamental purpose?
PSA's purpose is to enforce security standards on pods at the time of their creation. So this is all about the configuration and the behavior of the workload at runtime.
Okay, so Harbor checks the image contents, and PSA checks the deployment manifest. What kind of behaviors is PSA looking for?
It's enforcing defined security profiles, like baseline or restricted. These profiles dictate things like preventing privileged containers or restricting access to the host file system.
Ah, so no host path volumes.
Exactly. It adds that necessary layer of defense. Even if a developer somehow bypasses Harbor, PSA ensures the pod itself doesn't run with a dangerous configuration. It's deployment control on top of image control.
Okay, finally, even with all this security and HA, things can still go wrong. You need a safety net. In the vSphere with Tanzu world, why is Velero the go-to tool for disaster recovery?
Velero is used to provide backup and disaster recovery for Kubernetes cluster metadata and persistent volumes.
So why do you need Velero on top of, say, traditional VM backups? What is it protecting that a normal backup would miss?
A traditional backup protects the infrastructure. The VM's Velero protects the application itself, which in Kubernetes means the cluster state.
The YAML.
All the YAML definitions, deployments, services, config maps. If you lose the cluster, just restoring the worker VMs doesn't bring back the intelligence of the cluster. Valero lets you restore the entire application stack, and crucially, it integrates with vSphere storage to make sure the persistent data, the PVs, are snapped and restored right alongside it. You have to protect both the metadata and the data.
Shifting gears now to day 2 operations, handling growth and, keeping the lights on.
Right, scaling and observability.
So when we need more capacity in a Tanzu Kubernetes grid cluster, what actually mechanically happens when you scale up a node pool?
When you scale up a node pool, the system simply provisions additional worker node virtual machines to the cluster.
That sounds simple, but that automation is a huge feature of VCF and Tanzu. It's infrastructure responding directly to application demand. What's driving that provisioning?
That's the cluster API, or key API. It's the mechanism Kubernetes uses to manage its own infrastructure. When you change the node pool definition from, say, 5 nodes to 8, CPI sees that change and tells vSphere to provision 3 new worker VMs.
And they just join the cluster automatically.
They boot up, register with the supervisor cluster, and join the TKG cluster ready for workloads.
Yeah.
It's infrastructure as code enabling elastic, non-disruptive scaling. It's really slick.
So what does this all mean? Once you have this huge, resilient, secure thing running, you need visibility. How does a tool like VMware Area Operations for Logs help an ops team in this complex environment?
It helps by centralizing and analyzing logs from Kubernetes nodes, pods, VCF components, and all the underlying infrastructure for correlated troubleshooting.
That correlation is the key word there, isn't it? Because a pod failure could be caused by an NSX rule, which is logging an error on a totally different server.
Precisely. Without centralization, you'd be accessing into dozens of nodes, tailing logs, trying to cross-reference timestamps with vCenter events.
Yeah.
It's a nightmare. Area Operations for Logs just aggregates everything from the ESXi kernel right up to the app containers into one place. It lets you instantly correlate an app crash with, say, a resource constraint in vCenter. It turns a day-long troubleshooting exercise into minutes. Hopefully this deep dive gave you the tools to start solving it.
Thanks for diving deep with us. We'll catch you on the next deep dive.